So now that we've taken a look at what a linear function looks like in graphic form, or how we can determine the graphic form of a linear equation, whether it's being graphed out or whether it is we are graphing it ourselves. Now let's take a look at what we consider to be linear functions and contextual problems. So let's remember that some problems can be solved using linear equations or linear functions to represent a situation, or a contextual situation is what I might also call it. Okay, so we have some sort of context involved. We can represent that using a linear equation as long as it is a linear pattern, so it's going up by a consistent amount. Now, when a straight line graph is drawn from the information, it can be represented by a linear equation. Okay. So what we're going to do here is we're going to take a look at a situation that is graphed out, and can we create a linear equation from that graph. Now, here's the example. A cell phone plan charges a monthly fee that covers the cost of the first 300 minutes of phone use. It's a little bit dated here when we talk about minutes. Probably should be data these days. But let's say it covers the first 300 minutes of phone use, and this graph represents the cost of the plan based on time above or beyond the 300 minutes. So here we have a plan that the first 300 minutes of time spent on the phone, or if we want to consider it to be data, we could change that to gigabytes, is covered under the cell phone plan, but everything on top of that gets charged a little bit. So our graph here shows the time that's used beyond the 300 minutes, so it's in minutes. So this is 0, 20, 40, 60, 80, 100, and 120. That's the number of minutes. This is our X value right here. And then our Y value over here is going to be the cost that we're going to have. So you'll notice that this whole graph starts at this point here, 0, 20. So for 0 minutes over, you're going to spend 20 bucks on the plan. As the amount of minutes go up, the cost is going to go up as well. And we could say that this is another point on our graph here. This is at 150. Okay, so 150 is going to be that point, 150. Now, do we think, or do we know that this graph is of a linear function? Well, yes. Okay, it is a straight line pattern. Okay, it's a straight line. Okay, it represents a straight line pattern. That means it's going to be a linear equation or a linear function. Okay, it's a pattern. A linear pattern is the other way that we could look at it. Now, what does the slope of the graph represent? Well, the slope represents, okay, it's always, so M is always rise over run. The rise is going to be the change in cost over the time used, okay, and in minutes. So we could think of this as the cost per minute, okay, is going to be our rate of change. It's the cost per minute. It's how much is the cost going up based on how many minutes we're going to be using. Now, to come up with an equation for this, we need to figure out what is our M value and what is our B value. The B value is pretty straightforward. That's where it meets here. That's at 20. Okay, it's labeled as 20. Don't worry about the lines. It's labeled at 20. So B is 20. There's a mistake right there. Okay, 20. All right. And the slope is going to be the rise over run. And I have these 2 points. There's other ones that we could use in and amongst there, but we're going to use these two right here. So the rise is going to be this here, and the run is going to be this piece right here. Okay, the rise and run. The rise goes from 20 to 50. So we don't just count boxes. We look at it goes from 20 to 50. So this is a rise of 30. And the run goes from 0 to 100. So it is a run of 100. So our slope then is going to be 30 over 100, rise over run, which we can simplify to 3 over 10. Now, once we know this here, we can plug this into our form. Okay, and our form is y equals mx plus b. And so we're going to plug it in. Y is equal to 3 over 10x plus 20. Now this is an equation that's going to tell us how much it costs for the cell phone plan for every month. Depending on the number of minutes over will give us a total cost. Now you'll notice that we have a couple of other variables that are given, n and c. We could write that out as well. The cost is equal to 3 over 10 n plus 20, where n is the number of minutes and c is the cost. Now so that would give us, again, a couple different ways that we can write it out. Now, is this equation correct? We're going to look at another point right here. Here's the point 50, 35. Okay, there's the point. It looks like it's on the line. We're going to assume that it is. Let's see, is it actually correct? So if we plug it into our equation here, we're going to have 35 is equal to 3 over 10 times 50. Now I've plugged in, so this is the point 50, 35. I plug the 35 in for y, and I plug the 50 in for x, plus 20. Okay, in our calculators, what we're going to do is we know that this side has to be 35, so these two pieces here, when we put them together, 3 over 10, I'm going to do it as a fraction there, 3 over 10, you can do 3 divided by 10 too, times 50 plus 20 gives 35, so 35 equals 35. That is verifying that this is in fact correct. Okay, so it verifies that it's in fact correct. That point on the graph also works for the equation. It's not just one of the other points that works. Now, just as a little bit of a reminder, let's take a look at our slope again. The slope of this line, okay, represents the rate of change, okay, in the graph. And in the case above, like we said, it represents the cost per minute. And when we get context, we could always have some sort of rate of change that is given. It could be given as in words. It could also just be given as a number. The slope represents how much the linear function is rising or falling compared to the horizontal change. Okay. And now again, as a couple examples here, slopes can represent the y per x of the graph, or the change in y over the change in x of the graph. Okay, some examples that we could have some speed ones, so kilometers per hour, distance time graph. We could have the number of dollars per minute, okay, could represent that as well. Or again, like meters per second is also distance time. These are all ways that we could kind of represent our slope, okay, depending on the slope that we're given. In the case above, the y-intercept represents the base cost of the graph. Okay, it's a base, that's where it starts. The y-intercept is the place where the graph often starts, okay, because often we have like time or money below 0, okay, or the value when the x variable is equal to 0. Okay, so it represents where the x value is equal to 0. Once an equation has been made for a linear function, any value along the graph can be determined, okay, depending on what we want. Okay, if we're given a value of x, we can find the y. If we're given a value of y, we can find the x, okay, along those lines. And we place the given information into the formula in place of the variable, and then we solve for the other variable. Now I want to go back to this one just for a minute, and I want to go look at domain and range as well. I forgot to do those over here. So our domain and range. Okay, domain, again, is all the x values. Here's where it's starting. We can't have time below 0. So we're gonna say that our domain is x is greater than or equal to 0. And our range, okay, it starts here and goes up. So for our range, y is greater than or equal to 20, because we can't have it bill less than 20. But it can be anything over. It can be decimals as well. Sorry about that. So that's domain and range. We can put that in any situation as well, even if we're not asking for it. All right, so let's take a look at this one here. The student council sponsored a dance and a ticket costs $5 and the cost of the DJ was $300. Let's write an equation for the profit, P for dollars. Again, this will be Y based on the T tickets, and T is going to be X. Now let's, first thing we're going to do here is we're going to define our variables. So we have X is equal to the number of tickets, and Y is going to be the profit in dollars. Okay, so it's going to be the profit in dollars. Now our equation for this here is going to be based on these two numbers here. The first thing we need to know is what is our starting value, okay? So our starting profit, what is it, okay? And what is going to be our rate of change, okay? It's going to be based on the number of tickets. What are we multiplying to X? Okay, remember we have Y is equal to MX plus B. So B is our starting point. That's our Y-intercept. And that's based on profit, our starting profit. And M is going to represent the rate of change. So how are things changing based on the number of tickets that are sold? So in this case here, when every ticket we sell, we're going to make $5. So we're going to multiply every ticket by 5 to figure out how much profit we're going to get. The thing is, our starting profit, we pay $300. So this will be minus 300. So our equation will be Y is equal to 5X minus 300. Okay, that's what we're going to have as an equation there. Now again, we could write it out with P and T if we really wanted to as well, and I'll put that in there. So our profit is equal to 5T minus 300. If you want to do it like that, you can, as long as we know that P and T are Y and X. Okay. Now let's suppose that 123 people bought tickets. What was the profit? Well, if we have 123 tickets, that means X is 123. We plug it into the equation. Y is equal to 5 times 123 minus 300. Now we can do this without a calculator or with a calculator. Move that up a little bit so you can all see. Okay, 5 times 123 minus 300. And we're told that we have a profit of $315 from the sale of tickets and subtracting our DJ cost. Suppose the profit was $350. How many people bought tickets? Well, this means that our profit is now $350. So we're going to put that in. 350 is equal to 5x minus 300. Okay, we're going to have to work backwards a little bit in this case here. Okay, we're going to add 300 to both sides. So 650 is equal to 5x. Divide by 5, and x. So we're going to do 650 divided by 5. X is equal to 130 tickets sold. Okay, so we can then solve. If either we're given X, we can just plug it in and solve. If we're given Y, we're going to have to work our way backwards a little bit in order to solve, because we know something on the outside there. Now, could the profit be exactly $146? No, it can't be, because the profit will be a multiple of 5. Okay, 146 is not a multiple of 5. If you want to see this here, if we put profit in, 146 is equal to 5x minus 300. Okay, we're going to add 300 to both sides. I'm going to do this pretty quickly here. 446 is equal to 5x divided by 5. X is equal to 89.2. Okay, that should be a target. We can't sell part of a ticket. Okay, we can't sell part of a ticket, so we can't have a decimal in there. It has to be a whole number. On that note, our domain and range. Okay, so if we look at our domain and range, what is the domain and range of it? Well, our domain, we really could have any number, but we can't have decimals. So our domain X is going to be a part of the whole number system. Okay, so we could have 0, but we can't have a decimal number, so it's got to be above 0. And the range, okay, Y has to be greater than or equal to negative 300. That's going to be our starting point. negative 300 right there, starting point, okay, and that will be our range. Okay. All right, so you can continue on with the next video as I'll go through a couple more examples of linear functions.